Hello, good morning, good afternoon, wherever you happen to be around the world. This is Dr. Mohammed Nizami again, coming to you from Jerash, Jordan. Um, this is the second lecture in the series of analog to digital converter gigasamples per second type devices for use as a direct sampled RF receiver. Which has now the trend is RF to bits and bits to RF. Okay, I have my own YouTube channel where this lecture is at, and there are tens of hundreds of videos that I have posted recently um, on various topics of RF and microwave circuit designs. Um, I do offer a consulting service as a freelance designer from specifications or concept to system modeling, system validation, and then BCB based RF and microwave designs, anywhere from DC to 35 gigahertz. If you have any opportunities for such small projects, also modifying obsolescence boards with obsolescence devices that we could upgrade for you, the board. I basically turn in complete BCBA fab files to you with bill of material, BCB design, and everything. I work with you and the BCB house in China to produce the plain BCB, and then also to do PCB assembly. And then, of course, I would work with your engineers for testing and verification and further do any respins of the board if it needs to. Okay. So you could contact me at this number with a bunch of Android um, apps like WhatsApp and Telegram and so on. You can find me on there. You can find me on LinkedIn. Also, you could email me with this email right here. Okay. So previously, if you go to my channel, which I invite you to, please, if you can go to my channel and then you subscribe, you will find part one of this series. And I would really urgently ask you to watch that part before you watch this part, the second part, just simply because of the continuity, so that you have the complete picture and the complete background. You can find a whole bunch of videos on here of RF and microwave devices from LNAs to LNBs to waveguide designs, passive phase array distribution, antenna designs, microstrip antenna, magnetic materials. 3G and 6G transceivers, KU and KA, SATCOM, LMB, and buck designs, BCB transitions for high speed, transitions from waveguide to various types of coaxial of transmission lines, such as coaxial, SIW, and other forms as well, microstrip and strip line. Radial combiners and splitters, also both waveguide and coaxial. Microwave filters, waveguide and coaxial and printed. You can find videos on those designs. So please go ahead and visit my channel, and I urge you to go ahead and subscribe to the channel. I would appreciate that. That keeps me, as you know, motivated and keeps knowing that there is interest to produce more of these videos. Email me of any evolving concept that you'd like to, that you see a need to create a video on. I would appreciate that. Okay, so let's get back to, we're gonna cover two system designs today. And one of them is the S-band, and the other one is a millimeter 28 gigahertz type direct antenna to modem or antenna to bits and bits to antenna, which I'm hoping to create another series for that in the future. So previously we covered these three straight through text lines in here. Today we're going to cover, still continue on the principle of direct RF sampling receivers, and we're going to survey, look at the how, what is it that you need to build a receiver for these things, namely the SERDES, which are the high speed highway um, transporting hardware that is between the ADDs, high-speed ADDs, multi-giga samples per seconds, and then the rest of the DSP system. And then of course, the ADDs, we're going to survey those and look at what the current state of the market is. And then finally, I'm going to look at two examples today, um, just so that we can overview. But really, to go deep into the receiver front-end design, that's what's going to be happening in the third, fourth, and fifth parts that I'm looking forward to create those. Okay, so last time, as you know, we introduced a concept, which is basically take an RF modulated signal, pick it up via an antenna, and then filter the interferences out and so on, and bring the level up with using low noise amplifiers. And then conventionally, we used to do is we used to down convert this frequency, this carrier frequency, down to some intermediate frequency, IF, to be able to digitize it. Okay. Now, whether you digitize the baseband, you bring it down to zero IF, like direct conversion receivers, or high IF, in which you digitize it using an ADD, or you subsample it, meaning this IF in here could be either baseband, okay, or bassband, okay, and bassband that is in the first Nyquist zone, or it could be in the upper higher Nyquist zones, in which case we are doing subsampling, meaning we're really sampling a carrier frequency that is below the speed or the sampling frequency of the ADD, yet we are able to recover the baseband of that passband at the zero hertz frequency. And we're going to go through that today. Of course, in the other side, counterwise to this, is the other path. When we're transmitting, we're going really directly from bits to an RF on the antenna. And this is a future series. Okay, so I don't want to create a DSP class out of this, but let's just introduce few of the concepts that are really necessary to understand the operation of a direct sampled RF receiver. Now, on top here is a case where you're sampling a signal that has a bandwidth of at least a half, at most, I mean, a half the sampling frequency. Or likewise, you can say that you're sampling a signal whose bandwidth, okay, or the maximum frequency content of that signal you're digitizing is below twice it below the actually the you're sampling it as at twice at twice the highest frequency contents of that passband. I mean, and that's what we have here. In which case, that means really what you're doing is the frequencies in the analog world are just going to be transformed to the digital world, and there are no need for digital down convergence like we introduced last time. Okay, so that's easy done, and that's what people have done in the direct conversion receivers, basically, and some of the low IF sampling receivers. Now, a lot of times, of course, now you have to make sure that you're really, because the nature of the digitized signal, what happened when you digitize signal, you really convolve a baseband using a pulse, which is sampling. And therefore, when you convolve from basic linear system classes, you can see that when you convolve an impulse with a passband signal, you basically get a repetition. That pulse is going to be repeated at every so often, and then you're going to get exactly the same signal over and over and over. So it's a summation, the overall summation of the result is a convolved passband with an impulse, and therefore it's going to be sitting at the impulse everywhere. Okay. And that's what you see here. So that when you're digitizing a signal using FS, which is sampling frequency, you're going to get at every multiple of the half of the sampling frequency, you're going to get exactly a mirror image of two of the same signal. Now, one of them is desired, the other one is just an image. And of course, as you can see here, one of them is spectrally inverted, but still contains the same information. So um, if you have, if let's say that you digitize a signal that is like this, and you didn't want to utilize this part here, you want to utilize this part. All you need to do is just get a digital down converter and basically this here is 3/4 of the sample frequency. So you just rotate this down to here, and this will be rotated in the negative. Now, if you increase the sampling frequency, what happened is that that image that is here is going to go further and further away because your sampling frequency in here is going higher. So, which means that you can actually you can have an easy job of filtering just the desired signal in the first Nyquist zone. Okay. So this here really creates the concept of subsampling, which says that, of course, if it's true that you can sample, if you digitize a passband, you get exactly that same passband over and over and over, and depending on the and these regions are called Nyquist zones. They start out for the first Nyquist zone is basically if that signal happens to be below half of the sampling frequency, okay? And then the second one, Nyquist zone, is you get exactly the same signal but spectrally inverted in the area between the half of the sampling frequency to the sampling frequency, and so on. So what that means then, I could come in and my signal doesn't have to have to coincide with the first Nyquist zone. It can be anywhere as long as within the bandwidth, the 3 dB bandwidth of the ADD, and then I can digitize it. And then all I need to do is rotate it to baseband or go out with a digital filter and just basically pick any of these multiples of the same signal. And that's basically what this, a lot of people refer to this with this folding paper like in here. So what they do is you can look at the Nyquist zones, okay, at every multiple of the half of the sampling frequency. So you've got 0, and you've got the first half, okay, the twice the first half, which is sampling frequency, and then 3 halves, and then 4 halves, okay, and so on to the infinity. And now what happened is you can if an ADD is sampling at these signals in here at these rates, you can actually have an input signal as long as it's within the 3 dB bandwidth of the ADD, which has to do with the internal parasitic capacitance of the ADD and internal impedances. It has nothing to do with the internal the filters of the DSP or the aliasing filter. But of course, the aliasing filter has to extend and see that. You can actually move that analog signal. You can digitize the analog signal anywhere in here. And it's as if you fold them back, these Nyquist zones, they fold back and all get to be copied in the first Nyquist zone. Okay? All right. So, and that's really the principle of direct RF sampling, is because of the fact that you can subsample a signal, meaning that let's say you're trying to digitize a carrier signal that is modulated at 6 gigahertz, for instance. Well, at 6 gigahertz, you can come in and pick an ADD which has a 3 dB bandwidth above 6 gigahertz to be able to see that, capture that. And then the sampling frequency doesn't have to be actually 6 gigahertz. It can be, for instance, 2 gigahertz, okay? And if in that case, then all the aliases that fall within the zones that are within the bandwidth of the ADD, you can actually go into the DSP domain and figure out where that is and rotate it to baseband if you like to, okay? And that's the principle really of the direct RF sampling. So let's take an example. For instance, let's say that I have an analog IF, okay, which is at 156, or even a carrier modulated at 156 megahertz. And then I have the ADD at 125 megasamples per second. Well, let's draw the Nyquist zones. The sampling frequency is 125. So half of that, okay, is going to be 62.5. So this is the first zone, is from DC to 62. The second zone is between 125, which is this FS, and half FS, which is 62. And then the third one is, of course, the next one, which is 125 to 187.5. But guess what? That zone here is really where this IF is at. Okay? So now, again, we have an ADD where we're feeding it 156.25 megahertz sampled at 125 megasamples per second. From the Nyquist zone, and of course the dashed line in here is the bandwidth of the ADD, and we can see that the ADD starts deteriorating, starting above the fourth Nyquist zone region. So even this one in here, the way I drew it with the mouse, so I may have just did a little quick job on this, but let's assume that this was flatter than this, okay? And let me put this in you know. So now what we could do is when you digitize this signal, you are actually going to get the same information available at various zones as well. It does us no good to look at the zones that are above here, okay, because they're just going to be attenuated and distorted. But well, we can pick any of these ones in here, including this one, okay, and rotate it to baseband in here using a numerical controlled oscillator in the FPGA or the DSP. Of course, the digital downconverter, which is really to digitally downconvert the signal to baseband. That one used to be in the previous days, it used to be done in the FPGA, but now, or in ASICs, specialized ASICs, custom ASICs. But now it's really becoming a part of the ADD, okay? So what happens is you can pick either this or this or this, and of course, keep track that whichever one you pick, you really need to make sure that you're aware of the spectral inversion, which you can spectrally invert any signal via a very minimal mathematical equations like sign inversion of one of the I and the Q or swapping them. And you can look that up. I mean, we may go into it in the future, but you can look that up. Spectral inversion of signal using numerical methods, okay, in the DSP domain. So, and therefore, that's really exactly what's saying when you direct receive this signal here, okay? All right, even though we're sampling at a frequency that is below the location of the signal. So so this is the principle. Now, how did we figure out where these aliases are? There is a relationship which is really basically you take the center frequency of the signal being digitized, and you keep subtracting multiples of the Nyquist frequency, which is half of the sampling frequency. And that's where you're going to end up at these locations, basically. As you can see, the first one would be 156 minus 125. Which is really the sampling frequency. That's the third zone in here. And that's you're going to get 31.25, and that's where that first one is. Second one is here. So now in the DSP, if you want to rotate this to baseband, you could go and program your numerical control oscillator at this frequency, at the negative frequency of this, of course, or at the negative frequency of this, and then multiply it with the incoming signal. You've got a complex sample multiplied by a complex NCO, which is just sine cosine, just like a quadrature down converter, except it's done in the DSP. And you can work out, in fact, the ratio between the sampling frequency and the center frequency is such that you get a case where all you have to do is alternate between the sign of the I and Q, and therefore automatically you don't have to even do mathematical operations, which one of them, which is 4 times. So if you sample at 1/4 of the IF or 4 times the IF, you get that relationship. Okay, so we come in here and we say we want to disregard these, and we're going to get this part in here, okay, which is the first one in the Nyquist zone. And all we have to do now is we have to center this at baseband, and that basically is you take, this is the block that is available in the ADCs or in the FPGA. You take the streaming digitized signal and you just multiply it via this complex exponential sine wave in here, which is the NCO, e to the j 2 pi n, the numerical control oscillator frequency divided by the sample frequency, okay? And therefore, and that's basically what we're, in this case, this one sits at 31.25. We want to relate it to here. You program this guy here to which is direct digital synthesizer, to that, and you have a numerical multiplier in here that basically multiplies the ADD out via this one in here at the same data rate, and you end up with that. Of course, now, when you do this, you move this one to here, and this one to here, and that one to here. Now you've got a whole bunch of these aliases that you don't need, really. So the first thing you do is you hit it with a low-pass filter, and that way you get rid of all of these, okay? And that's shown in here, okay? So after you rotate it to baseband, you also hit it with a low-pass filter. And then, of course, it's oversampled, meaning the sample rate in here is way above the minimum required samples for the symbols to be decoded. And therefore, you can come in and start throwing out samples to reduce the complexity of the coming DSPs above that. And that's decimation filtering, okay? And we did introduce that in the last lecture and showed how the signal to noise ratio in here is going to be improved by exactly that ratio in here, 10 log of that ratio, because meaning if you decimate by 2, half of the samples are gone, then you improve by 3 dB. If you decimate by 4, you improve it by 6 dB, the SNR in here. And the SNR in here, the one we're talking about here, is really always within the SNR of the signal, but that is within the SNR of the ADD, which is from full scale down to the quantization noise, or above that by a certain range that we're going to show in the next session how you analyze all of that. Okay, let's take another example just for the heck of it. So here's a 28 gigahertz signal. Historically, in a case like this, how do we digitize this signal? Well, the easiest way to do this is that you come in and you say, well, if my ADDs, for instance, can only capture up to 8 gigahertz, what I could do is you can go and down convert the signal via mixing with 20 gigahertz low, and you get 8 gigahertz. And that 8 gigahertz, basically, you feed it into the ADD and you digitize it. And digitizing this, you really perform it either at some sampling or at at baseband, in the phase narco zone. And graphically in here, you can see how that is done. You can see what the issues that you are facing. And namely, the first one is we've got the LO, which is 20 gigahertz, but when this is your signal of interest at 28 gigahertz, you're always going to have an image in here, which is in this case at 12 gigahertz. So the first thing that what you want to do is you really want to make sure that this signal in here, you try to filter out the image, okay? And even if there is no image, just the broadband noise in here is going to be reciprocally down converted to the baseband. So you need to just filter out this and reject the LO um, and the image. And then you get to be at 8 gigahertz, which is this here. Now 8 gigahertz, you digitize it, and then that's where you actually get it to here. Now you could, if you want, do this. This is, of course, the super heterodyne receiver architecture. This is what this is methodology. And of course, you end up with all sorts of issues that are having to reject the yellow, and of course, you've got a very complex synthesizer and mixer and so on, and spurs and harmonics and so on. Now, as another option, what you could do is you can go to direct conversion, meaning your LO is running at the same frequency, and therefore you get a 0 hertz, a baseband signal, centered at 0 hertz, and then you digitize it. And that way, the easiest way to do this is you do this, of course, quadraturally, okay? And so you have a quadrature down converter that has a real the I and the Q, okay? And you do that by having an LO, which is basically a quadrature between 0 and 90 degrees. And you get the streams, the complex stream, which is the I and Q in here. But when you combine these to create the baseband signal, you're going to get a whole bunch of issues when you direct digitization of the zero IF or near zero IF that you're creating from the incoming modular carrier by direct conversion. Okay, and that's illustrated in this figure in here. First of all, since this frequency, same frequency as this, you're going to get a DC in here, and that DC is represented here by an impulse. Okay, that DC is basically, or even the LO that leaks in here is going to be actually transformed areas back to 0 hertz, and that's going to eat up a lot of the dynamic range issues in here. So if it's within the dynamic range, then you have to perform some digital signal processing algorithm to try to take out that DC, which is basically you keep estimating the mean of the I and the Q, and you just keep subtracting an offset from both in phase and out of phase branches. And then, of course, you got issues with the image, okay, because you have two separate channels in here digitizing, and there are mismatches going to be between all these the low pass filter, the amplifiers, and then the LOs here, the amplitude and the phase mismatches, and that creeps in as an image, so you receive it directly on top of your desired signal. And then if you have second order intermodulations, that also, once you go through the nonlinearities of the chain in here, it comes in at baseband as well. So therefore, this has a whole bunch of issues. So what do we do then? Well, the best way to do it is to go actually do direct digitization. But how do you do direct digitization? Well, here's an entity. And what I'm going to do, I'm going to basically digitize the signal that is coming in here direct on the 28 gigahertz. And how you do that with subsampling. For instance, in this case, the you could go to one of the commercial ADCs. Like in this case, I put in this EV10AS940, which is from E2V. That's an ADD that runs at 12.8 gigasamples per second. That's way below 28 gigahertz, but wait and see how it's going to be actually as effective as um, sampling this carrier here at multiples of this number. So what we do, we run this, and then if you run 12.8 gigasamples per second, if the sample frequency is 12.8 and the incoming signal is 28, well, just like we did here, where we show this one in here, if you look at the analyze the NACWA zones, it turns out that actually when you do this, you get if the ADD in here, the bandwidth of the AD, if it can pass signals that are on this order, you actually have one of the lowest replicas of this passband at this carrier is going to be centered right at 2.4 gigahertz. Okay. And in that case, that's voila, we're done. So all you need to do is pick that alias in here and you digitize, basically that's digitize. So you run it through a digital down converter running at 2.4 gigahertz and you bring it down to baseband and you're done. And that's pictorially, that's shown in here. So we've got a carrier signal that is running at this, okay? So we digitize it at 12.8 gigasamples per second. And then what happens with this one here, we look at the digital domain, one of the aliases is going to be at 2.4 gigahertz. And then what we do is we multiply it by an NCO, a numerical control oscillator, okay, or a digital down converter or digital synthesizer in here. We multiply it, and then of course this signal is complex, and this is complex, and we end up with a complex signal that is centered at 0 hertz, and we're done. Now, of course, the other aliases we reject them via filter. What we do here is we will have a bunch of filters in here, okay? And the most important thing is that this sampling rate here is, of course, huge. And we really don't have, if you look at any of the modulated signals, be it SATCOM signal or 6G or cellular, we don't have bandwidth that are required for half of that, which is at 6.4 gigahertz. We don't need all these samples. So the first thing is we hit this signal with is we decimate these samples. We could decimate, for instance, by 10, 100, or so on. Well, it has to be multiples of 2 to the n. And so you end up with an appropriate rate that you can feed it into the demodulator and be able to do that. Yeah. Okay, let's analyze this further. So basically what we did then is we looked at the spectrum. And if you look at the spectrum, basically, if you're digitizing at 12.8 gigasamples per second, and so what we're going to do is we're going to look for where that signal is going to be at, and then try to somehow in the DSP bring it to baseband. So if you have 12.8 gigasamples per second, the Nyquist frequency is actually the 6.4 gigahertz, which is one half of that. And then so every multiples of that one half, we're going to have a region. So when we look at this now, and assuming that the ADD really can capture such signals, and of course this EV10AS94, if you look at it, it has a bandwidth that can pass that signal. We located one of the, here's where the 28 gigahertz set is set. Okay, so what that is saying now is we're going to pick somehow this signal to be transformed to the baseband. And so if we look at this signals, we can see that the replicas that are below the 12.8 gigahertz gigasamples per second and above. And according to this equation in here, if you look at the fifth part, the fifth Nyquist zone, really 28 gigahertz minus n minus 1 of the Nyquist frequency, we could see that we're sitting at 2.4 gigahertz in the digital domain. So we have a digital IF that is at 2.4 gigahertz. And now what we need to do, we need to bring that to baseband. And so we need to pass it through a numerical controlled oscillator multiplied by it, which is basically a digital down converter. And that's so we need to bring this 2.4 gigahertz in here in the digital domain to baseband, and then do all the following decimations and filtering and so on. Okay? Now, so next, what we're going to do is let's look at through more of the ADCs that are available in this year, 2025, to be able to see what are the wireless services that we could build receivers for using the current state of the market in ADCs. Okay? And that's going to be in the next part, basically. So I'll see you in a moment where we're going to look at all these frequency allocations of the current wireless services, and then look at the ADDs from various companies. These are the main players: Texas Instruments, Analog Devices, E2V, AMD, which was really Xilinx before. So we're going to look through all of these and have a map and review these devices and see how we can build a direct sampling receiver. Okay, so until then, and of course, in the we're going to go through this example in here where we can show this using system view, and then finally we're going to end up by looking closer at the ADD signal dynamics range signal, and look at the signal to noise ratio and the harmonics, spuriouses, aliases, and start building a method by which we can actually design a direct RF sampled receiver. Okay, so I'll see you in the next part. Okay.